we got to the point in the last video where we got to the midpoint rule. We've developed an algorithm in MATLAB, and then we were able to come pretty close to an approximation. So we're going to be able to do the exact same thing now with Simpsons Rule. All right. And the trick with Simpsons Rule is that it's a little bit different than midpoint because now we have to have these alternating 4s and 2s, but we also have to have the endpoints. All right. And the endpoints are pretty easy to take care of. We can't forget about b minus a over 3n for our delta. All right, so let's get to it. And the good news is we can just use a lot of what we had from before. So we already have everything that we had, the input. Now I am going to redefine delta, all right, because if we don't have delta redefined, then it's not going to help us too much. So let's redefine delta as b minus a, and we're going to divide it now by 3 to n. Okay. All right. And now let's go ahead and start to figure out what to do with Simpsons. And here's what I'm going to do. I'm going to do this in 3 parts. All right. So this is going to be the endpoints. And this is going to be, I'm just going to call it simp. And simp is going to be equal to, when we substitute back into the function, the old value is x, and we're going to substitute the initial value a. And then plus, we're going to substitute back into f. The old variable is x, and the new value is b. All right, and that's going to take care of the endpoints. All right, and by the way, at the end, what we can do is we can just multiply by delta to get where our Simpsons is going to be. Now we're going to take care of the multiples of 2 or 4, excuse me. All right, or maybe we could say the coefficients that have 4. Okay, so that's in our formula. When we're looking at it, we have all of these, and remember, these are the odd terms. All right, so if we can start with the odd indexes, then what we can do is we can just go ahead and say, okay, well, I'm going to multiply all of those by the function evaluated, and then multiply it by 4. So here's what I'm going to do. I'm going to make a for loop. And I'm going to say for I equals a plus delta. All right. And the reason I do that, well, let's do this. I'm going to get rid of this delta. And we know that our delta from earlier is just going to be b minus a over n. So what we can do at the end is we can multiply by delta over 3. So a plus delta is going to give us the next I. Okay, so we're going to say that, and then we're going to say 2 times delta. All right, and then we're going to say for the last one, this is going to be b minus delta. All right, now the coefficients of 4 are in the odd indexes. All right, so basically what this is going to do is it's going to start 1 value up from A and 1 value behind B, which are the 2 endpoints. And remember, in the formula, the 4s are sandwiching those endpoints. And this is just going to make sure that it's going to be odd, skip even, odd, skip even. All right. And once we're done, I'll show you that it does work pretty nicely. And we're going to say simp is going to be equal to the Simpsons that was previous plus, we're going to say 4 times subs of f comma x comma I. All right, and what's that going to do? That's going to say every other index that's odd, we're going to multiply it by 4. All right, and then we're going to end this. Now we still haven't taken care of the even indexes. All right, so these are going to be for the coefficients of 2. In other words, the even indexes. All right, and to be able to get that, we're going to build another for loop. So we're going to say for I equals a plus 2 delta. All right, so now we're starting at 2 terms ahead. All right, and that's going to be in terms of delta, or 2 times delta, excuse me, because we want it to be every other one. And then we're going to say b minus 2 delta. And we're going to do the exact same thing. We're going to say simp is going to be equal to the previous simp plus 2 times the subs of f comma x comma I. And then the last thing that we have to do is we have to multiply by that delta. And remember, our delta in this case is going to be delta b minus a over 3n. All right, so for the last one, what we're going to do is we're going to say simp is going to be equal to simp times delta divided by 3. All right, and what that's going to do is if we go back, that's going to take care of this 3n. Remember, delta is b minus a over n. I'm just now multiplying it by another 3. Okay. All right. Now, of course, the proof is when we go to actually print this. All right. So we're going to find the percent error. So I'm just going to copy these statements because these are the ones from before. And I'm just going to call this simp error. All right. And that's going to be equal to simp minus actual. And then this is going to be simp. And this is going to be simp error. And right here, we are going to change this to Simpson estimate. All right. So let's give this a whirl. Let's see if it does anything good for us or not. Right, so I'm going to run it. And let's just do something really basic. So we get x squared. Let's do from, let's say, 1 to 4. And let's do something like 250 subdivisions. All right. It might take a moment. All right, so here's our midpoint rule, which we know works. And now here's our Simpsons rule. All right. And notice that the Simpsons rule is even more accurate than the percent error of the midpoint rule. All right. So notice the midpoint rule has a piddling error, of course, of somewhere in the 10 thousandths, which is really good to begin with. But with the same number of iterations, the Simpson estimate's even better. All right. So hopefully you can see how this algorithm works. All right. So, and if you're trying to do the trapezoidal rule, what you're going to do is you're going to take care of the endpoints, and then you're just going to start one index in and then one index behind, and you just multiply everything by 2. All right. So you're going to use something like this algorithm, except it's not going to be 2 delta. It's just going to be every delta, and you're just going to multiply by 2 in here. All right. So a lot of this code is going to be helpful for being able to take care of the trapezoidal rule. All right, now, the last part of the problem is we're asked to apply it, all right? And we are asked to find the probability of an iron ore sample given by this integral. So it's 1155 over 32x cubed, 1 minus x to the 3/2 power. Certainly not an integral that we want to evaluate. In fact, we don't even know if it's possible, but we're just going to use both of the programs, and we're going to see if both of them can approximate the probability that a sample will contain between 0 and 25% iron, and we're going to use 1,000 partitions. This should get us really close. With 2 strong algorithms, we should be able to figure this out pretty well. All right, so let's go to it. We're going to say, first of all, we're going to run this. And we're going to input, so we're going to say 1155 divided by 32 times x cubed times 1 minus x raised to the 3/2. So that's our function. That's nice and easy, right? Now we're going to enter the lower bound, which is 0. Now be careful. It's 25%, so we need to put it in as 0.25. Notice if you put it in as 25, you're going to get 1 minus 25 raised to the 3/2. You're going to be taking the square root of a negative number. That's not going to work. All right. And we did say, so this might not work because I put an x in there by accident. So let's just try running it again. I just made a faulty input. All right. So here's our input. The lower bound is 0, 0.25 is the upper bound, and we have 1,000 subdivisions. All right. So it might take a moment just because we have 1,000 subdivisions, and this is kind of ugly. And I don't even know if this is evaluable. I'm certain we could do a U substitution, and then so it is evaluable at least. All right. So the midpoint estimate at least accurate to the tens, hundreds, thousands, 10,000s, 100,000, millions places. Good. Same thing with the Simpsons estimate, except the Simpsons estimate's a little bit stronger. Okay, so this has what, 38 millionths or something like that, or 3,800 thousandths, and this percent error is actually 0. So what we can say is that there's about a 2.5% probability regardless of which of these we use. All right, now the actual value is right here, which tells us that, but there might be problems where it's just too difficult for us or even MATLAB to be able to compute the exact value. So hopefully you can see the validity and the necessity of utilizing these numerical methods to be able to help us evaluate some of these types of problems where, quite frankly, integration utilizing analytic methods is just too difficult. Right. So the last thing we're going to do is we're going to look at uneven types of segments. All right, and we'll do that in the next video. But again, hopefully this helps you to understand the algorithms. And again, you'll have to write this for the trapezoidal rule. Just utilize some of the same code and just change a few of the parameters so that way you can be able to do that.